Welcome. So this should be my last podcast for graphing exponential growth and decay in logarithms. And in this podcast, we're going to be looking at translating and stretching and shrinking logarithms. Now this might be one podcast, it might be two podcasts. We'll see. All right, so first of all, we're going to look at the transformations, and then we'll look at the stretching and the reflecting. All right, so, and here I'm just kind of showing you what it will look like, and then we'll actually do it. All right, so vertical shifts. All right, so moves the same as all the other functions. If you add something to the whole function and it's positive, it goes up. If you subtract something from the whole function, it goes down. All right, so the value, it's just a hint here how you can figure it out. The value added or subtracted is not in parentheses. All right, so if you have anything added or subtracted and it is not in parentheses, it is a vertical shift. Horizontal must be tied to the x. And the only way to tie it to the x is parentheses, right? The vertical shifts really don't change much of anything except move the graph up and down, right? Isn't going to change your vertical asymptote, isn't going to change domain and range, just going to move the function up and down. All right, so here we have in blue the base function right here. Here we'll draw an arrow that'll point to all our functions because I can point, but you can't see me. All right, so y equals log of x. There's that graph there. Remember how we get that one? To graph that, we take 10 to the y equals x. Right? So the y's are the exponents, and the x's are the results after you raise 10 to a power. And it takes this graph a long time to grow. You notice it didn't even hit 1 yet on the y. That's because it's got to make it all the way to 10 before it gets to 1. It's got to make it all the way to 100 before it gets to 2, and 1,000 before it gets to 3. So really slow moving graph here. But anyway, here we have the original function, right? It's going to, base graph has no translation, so it is going to go through the point 0, 1. 1, 0. And then if we want y equals log x plus 3, right, that's going to move our graph up 3. Come on, arrow. Oh my goodness, come on, move, 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 move. There we go. What purpose are you if you don't move and point for me? All right, so our graph is going to move up 3 units, all right? So notice the point here. So over here it was at 1, 0. On the red graph, right, just add 3 to it, right? So instead of at 1, 0, it's going to be at 1, 3. Just add 3 to the y. Right? And then we could also shift the function down. Here we have y equals log x minus 4. So now that point is shifted down 4. So now we have the point 1, negative 4. Right? But no other real changes. Right? So just if you have something add or subtracted to the function, if it's positive, just graph your base graph and count up. If it's negative, take your base graph and count down. That's all there is to it. Right, so now let's look at another type of transformation. And that should be, oops, for some reason I guess I have this twice. Well, that's okay, once was good enough for me. And let's try it again. Horizontal shifts, there we go. All right, so horizontal shift moves the same as all the other functions, right? It's got to be hooked on to the x value, right? So it has to be in parentheses, right? Hopefully you can read the red here. Quite honestly, should have chose yellow. Look how much nicer yellow is, right? So I can maybe go over it. The value, does that make it better? The value added, subtracted, is in the parentheses. Maybe I should have erased the red words. Trying to outline my words. Right, so that's going to be a horizontal shift. But you'd be amazed at how hard it is to write the same each time. There we go. Better? I think it looks a little better. Maybe next I'm going to erase the red. It has this weird kind of red glow to it. All All right, so now it's going to change. It's going to change our vertical asymptote. It's going to change our range. All right, so here are the blue again, and we'll use a purple arrow. There we go. All right, so in the blue there we have y equals log of x. All right, and same base graph we saw on the last page. Right. If we have y equals log in parentheses x plus 2, right, adding something to x shifts it to the left, right? Because now, if I have, so for instance, if I want that to be 1, right, I just got to plug a 1 in. But with that plus 2, if I want it to be 1, now I only need a negative 1. So do you see how that's 2 smaller? Right? So now a negative 1, if x is negative 1, that would also be a 1, right? Because negative 1 plus 2 is 1. Right? So it's going to shift it to the left. This takes a smaller value if you go and add something positive to x. And if it's a minus, then it's going to move it to the right because it's going to take a larger value. Right? So y equals log base x minus 4. So y equals log x plus 2, all in parentheses there, goes through the point negative 1, 0. Y equals log x goes through the point 1, 0. Right, so that's shifted 2 to the left. And y equals log x minus 4, that's going to shift 4 to the right. So that goes to the point 5, 0. Right? 4 more. So all you have to do is count. Right? So if it's positive, count to the left. If it's negative, count to the right. And that's all you got to do. Right? And whatever that horizontal transformation is, it's also your vertical asymptote. So let's write that down. So, and by the way, none of these are all in your notes. And I think all the writing is too. Sorry, it's red. So the vertical asymptote. Well, I could put horizontal shift. I'll start with horizontal. Horizontal shift equals vertical asymptote. Right, so whatever that is, that's going to be your vertical asymptote. Let's continue on. And now we have reflections. All right. So and all of these are in your notes, every bit of them. All right, so here we have g of x equals negative log base b of x. If it's negative in front, it's going to reflect it about the x-axis, right? Because you're just taking a positive number times a negative number, right? So of course it's going to make it negative. If you if the negative is inside the radical, it's going to reflect about the y-axis. You can only take the log of a positive number, because when you raise a base to a power, you get nothing but positive numbers. So you can only take a log of a positive number. Right? So if you've got y equals log negative x, right? X has to be all negative numbers. Right? Because a negative times a negative is a positive. Right? So here you can only plug in negative numbers. Right? That's why if it's negatives on the x, it's going to reflect it over the y-axis, right? And that's true for all of our functions. If the negatives on the x, reflects over the y-axis. That was true for our radical functions. The negatives in front, it's going to reflect over the x-axis. And then I think I got stretches in here. Yeah, vertical stretching and shrinking. All right. So we have vertical stretch. All right. So here we have y equals 5 log of x. This one is vertically stretched. Right? And that's because that coefficient, C there, equals 5, and 5 is greater than 1. Right? So it's going to grow faster. That's why. So it's vertically stretched, it'll grow faster. Right? Here we have y equals 1/5 log of x. This one is vertically shrunk. Right? Because C here is 1/5, and 1/5 is between 0 and 1. So it's going to grow more slowly. Right? If you take some number and you multiply it by 1/5, you're going to have 1/5 as much. It's going to be smaller. Right? You multiply by 5, it's going to get bigger. And actually, I'll show you how to deal with these. The vertical stretching and shrinking actually is not difficult at all. It will not be part of our base graph. We'll have our base graph, and then we'll deal with shrinking and stretching. My page isn't turning. There we go. That was a very delayed reaction from the board. And it's turning right now, maybe? It's thinking about it. There we go. Horizontal stretching and shrinking. So unlike vertical stretching and shrinking, horizontal stretching and shrinking is going to be part of our base, right? It's easier to deal with that way. It's actually easier to deal with vertical, not part of the base. It's easier to deal with horizontal as part of the base. I decided it was going to go 2 pages. Well, I haven't gone up to this page. I'm not done yet. Move back. Go back to the page I was on. There we go. All right, so here we have a log and some base. And if the coefficient on x is greater than 1, it's going to shrink the graph, right? Because it takes a smaller value to get to the same place, right? So this one shrinks the graph. This is a horizontal shrink. Right? And it's going to shrink by, since that's 5, it's going to shrink by 1/5. Y equals log 0.5x. That's going to be a horizontal stretch. With that 1/2 there, oops, you're going to stretch by a value of 2, because now you need a value twice as big. Over here, y equals log 5x, I only need a value 1/5 as big to get to the same place. And it'd be nice if I spelled stretch right. So this is a horizontal stretch, right? And that's going to stretch by factor of 2. It's going to grow twice as fast horizontally, right? Because I'm going to need twice as big a number to get to the same place. Right? That we're going to deal with on our base graph. So you can put in your notes here. You can just consider as part of the base graph. That's the only one. Right? So now let's look at domain and range, which is the last of the pages, and all of these are in your notes. And you should add the things that I write in. You can pause the tape, or you can just write while I'm waiting for the page to turn. There we go. All right, so domain. Because a logarithmic function reverses the domain and range of the exponential function, the domain of a logarithmic function is a set of all positive real numbers, 0 to infinity, unless a horizontal shift is involved. All right? So, oops. Let's see if we can get my numbers to be in the right spot. There we go. All right, so if for y equals log, and we saw these on the previous page, but for y equals log of x plus 2, our domain is now -2 to infinity because we've shifted it 2 to the left. Normally, the domain is going to be 0 to infinity, but if you shift to the left, you're going to change the domain, just like if you shift to the right. So y equals log x minus 4, that shifts 4 to the right. Our domain is 4 to infinity. Regardless of whatever shifts we have, our range never changes. So the domain is restricted, but the range is the exponents, and the exponents can be anything. So your range is always -infinity to infinity are all real numbers, right? And that's true all the time. It doesn't matter what kind of stretches you have. stretches or shrinks or shifts, or doesn't matter. Doesn't matter. All right, so now let's get into some graphing now that we've looked at what they look like. Now let's do it. All right, and you'll have all of these in your notes. Once my podcast gets to about the 30-minute mark, I'm going to split it into two. It may still go on the same Nearpod, but I'll still split it into two. All right, so we want to graph at g of x equals log base 4 of x plus 4. Our base function does not include the plus 4. It's everything else. All right, so now let's rewrite it as an exponential. That's our first step. All right, so that's going to be 4 to the y equals x. That's our related exponential. So we just plug in for y and solve for x. Let's take -1, 0, and 1. Anything else is going to be too big, right? Because these are exponents. If I raise 4 to the second power, I'm going to get 16, and that does not fit on this graph. All right, so we have 4 to the -1. That's going to be 1/4. That's plenty small. 4 to the 0 is 1, and 4 to the first is 4. This is the minimum number of points you can graph. And if you can graph more, do so, but sometimes you can't. 1/4, -1, 1, 0. Sometimes on graph paper you can get more spaces, but not on a coordinate plane where I give it to you. And 4, 1. Those are our points. Let's graph those. All right, so we have 1/4, -1, and 1, 0, and 4, 1. All right, so here is our graph. We know that it has a vertical asymptote. Oh, here's our base graph, excuse me. We know it has a vertical asymptote. I need my pen to stop being yellow. There we go. Of x equals 0. Right? Now we're going to graph the function we want to graph, which is g of x equals log base 4 of x plus 4. All that's going to do is shift our graph up 4. So if I just shift it up 4, 1, 2, 3, 4, it's not going to change 1, 2, 3, 4. The vertical asymptote, it's not going to change the domain and range. Nothing's going to change other than the points are going to be shifted up 4. There we go. I went just a little high. There we go. That looks a little bit better. So vertical asymptote, same as on the base graph. Our vertical asymptote is just x equals 0. Right? And the domain, 0 to infinity. And the range, -infinity to infinity. And that's all there was to it. All right? That wasn't too difficult, was it? Nah. You rewrite, you plug in 3 numbers, you graph the 3 numbers, you count it to 4. Not too bad. Let's graph another one. There we go. All right, so we have g of x equals log. Our base is 1/2 of x minus 2. All right, so base graph is g of x equals log base 1/2 of x. All right, it's not going to include any shifting. All right, that's not part of our base graph. The only thing that we're going to include as part of our base graph, besides the base graph, just that that base, that simple little log graph, is if we have a horizontal stretch or shrink. That we will include as part of it, right? Because it's a lot easier to do it that way. All right, so first of all, let's rewrite it as an exponential. Once you get the hang of graphing a few functions, you'll find out that a lot of them are very, very similar. So, oops, that's not very easy to read. Other than this one step, it's not very different than the exponentials. I mean, and the translating is not any different than the radicals, except it's a different function, but the translating is a lot the same. So here we have 1/2 to the y equals x. All right, so we're going to plug in for y. Now this one is this one is a little faster growing on the x, so we could plug in some more values. We could go all the way to -3. All right, we should do -3. -2, -1, 0, 1. All right, so you'll figure out, I think, pretty quickly what values you should use. 1/2 and 2, you want 0, 1, 3, 2, 1, 0, 1. If it's 1/2, you want most of them to be negative. If it's 2, you want most of them to be positive. It would just be the other way around on sign. All right, so 1/2 to the negative 3 power, that's like 2 cubed. That's a negative in there, which is 8. 1/2 to the negative 2, that's like 2 squared, so that's going to be 4. 1/2 to the negative 1 power is just going to flip that, so that's 2. Anything to the 0 power is 1, and 1/2 to the first power, that's 1/2. So our points that we're graphing are 8, -3, 4, -2, 2, -1, 1, 0, and 1/2, 1. All right, this is decay, so it's going to decrease. All right, and we went over the decreasing. We should go over maybe the end behavior. All right, I think we'll do that, and I'll go back to the other graph. We'll do the end behavior. All right, so again, here is where our vertical asymptote is right now on our base graph. All right, so we're graphing the points 8, -3, so 1, 2, 3, 4, 5, 6, 7, 8, -3, and 4, -2, and 2, -1, 1, 0, and 1/2, 1. All right, so it decreases. Anytime it's decay, it's going to be decreasing. There we go. All right, and now let's graph our, let's do the translation. All right, so we're shifting 2 to the right. Right, we got a minus. It's hooked onto the x, so it's got to go right or left, and it's a minus, so it's going to go right. That is going to change our vertical asymptote. So now we're going to have a vertical asymptote at 2 instead. All right, so let's graph that. Actually, that's right in our asymptote. X equals 2, and now let's graph that. Our points are just going to shift 2 to the right. So everybody goes 2 to the right. You go 2, you go 2, and where's the next one? Right there. You go 2. Oh, I skipped somebody. You go 2. You go 2. Everybody goes 2. And there we go. So the domain now is 2 to infinity. The range is still all real numbers. Let's do end behavior, because I didn't do that on this one, and then we can go back and do it on the other one. All right, so our function approaches what as x approaches negative infinity. Right, so as we approach negative infinity, right, and actually we don't even get to negative infinity, do we? Does x get to negative infinity? No. How far does our function go? Well, the smallest our function goes is 2. Remember, we got that restricted domain, right? So 2 to infinity, right? So silly me. I started to put down negative infinity because you get used to doing that, and then you look at your function and go, whoa, that's right. I'm graphing a log function. It's got the restricted domain. All right, so as we get close to 2, our function is going to infinity, right? As I get close to that vertical asymptote, it's going to get bigger, larger, and larger. As we move away from the asymptote, right, my function is going to grow to negative infinity as x approaches infinity. Right, so x is going from 2 to infinity. Right, so this is the domain. Right, so this matches domain. Actually, I'll write it down here. All right, so it can't be anything different than your domain, the 2 to infinity. And this part here matches range, right? So the range was all real numbers. All right, and that's it. We've graphed it. All right, the red graph there is g of x equals log base 1/2 of x minus 2. We've done the end behavior. We're all done. Let's go back to the other graph and just put in the end behavior. Good practice there. All right, and this one is a little easier, I think, because it's growth. It's getting larger, right? We've got a base that's larger than 1. And we didn't even have a shift. So here our end behavior, f of x approaches. So the closest x is going to head to is 0. All right, so x heads to 0, and x heads to infinity. Right? It doesn't get any, that's it, right? It tries to get close, it gets closer and closer to 0, but it never reaches it. And it never goes past that line. And as it gets close to 0, the function's getting close to negative infinity, right? It's going down. And as x goes to infinity, so is our function. It takes a sweet old time, but it does head towards infinity. Right? Let's do another one. Let's graph another one. All right. And move on. There we go. We've already done this one. Let's go to this one. Here we go. Any day now. Any day now. There we go. All right. So now we got two shiftings. All right. So our base graph, it doesn't include any of those shiftings. All right. So our related exponential. So we're going to write it as an exponential. We have 5 to the y equals x. Right? Here you can't plug in too much. Right? Base isn't 2 or 3. You don't get to plug in too much before it gets too big. Right? So 5 to the negative 1 is 1/5. It's just the reciprocal. Anything to the 0 is 1, and 5 to the first is 5. So that means our points are 1/5 negative 1. 1, 0, and 5, 1. I find this really helpful, especially, oops, 5, 1. I said 5, 1. I find this really helpful to write those points down, especially for me at the board, because it's easy for me to read them backwards, right? Because I'm actually standing to the right of those values, and sometimes I just want to read them backwards. All right, so it helps me from doing that. 1/5, negative 1's right there. 1, 0. And 5, 1. Right? We won't hit 2 for y until we get all the way to 25. So make sure you don't cross 2 because it takes a while. All right, so now our graph has been translated. All right, so 2 to the left, right, that plus 2 moves 2 to the left, and the minus 4 moves it down 4. All right, so let's first of all graph our new vertical asymptote. All right, so for shifting to the left 2 means we have a vertical asymptote at x equals negative 2. Now let's just move all our points. 2 to the left and 4 down, all 3 of them. All right, so 2 to the left and 1, 2, 3, 4. There it is. And 1, 2, 1, 2, 3, 4. And last but not least, 1, 2, 1, 2, 3, 4. There we go. We've moved our 3 points. All right, it's going to head to the asymptote, and then it's going to turn. There we go. And eventually, it will keep growing. Just takes a while. All right, domain. Our domain is changed, right, because we shifted 2 to the left. Now that's oops. I am saying negative 2. Does that look like a negative 2? Negative 2 to infinity. Sometimes, I swear, my hand does not listen. I'm saying one thing. It says, hey, let's write something else. Negative infinity to infinity is our range. Let's do an end behavior on this one. All right? So I think that's good practice. All right? And so oops, x is going to approach, right? It's going to follow its domain, right? So the smallest number in the domain, negative 2. Right? So, oops. I get the eraser, and it changes my color. As x approaches negative 2, I just want to make it negative infinities, I guess. And as x approaches infinity. All right, so what happens as the function gets close to negative 2? All right, so your function is going to head to negative infinity, right, as it gets closer and closer to the asymptote. So always, actually, if your base is greater than 1, it's always going to be negative infinity as you get close to that asymptote, and infinity as you go towards the asymptote. Away from the asymptote. Right? So as you go towards the asymptote for a base greater than 1, it's going to head towards negative infinity. And when the base is greater than 1, as x approaches positive infinity, your function's going to head to positive infinity too. If this were decay, right, then instead of heading towards negative infinity, it'd head towards positive infinity as it headed toward the asymptote, and then it would head towards negative infinity as x approaches infinity. Hopefully that's clear. I'll try very hard not to mumble my words or anything like that. And now we're waiting for the next graph. All right, so we're going to do, let's see how many we have before I decide whether or not I'm going to split this. We got 1. We got 2. And then we actually got a little bit more. And then we got kind of a couple transformations there, 3. So I think this is a good place to split this lesson. All right, so I'm going to split the lesson because we've got lots of other things, more transformations, we've got natural log, all kinds of things. So I'm going to end this lesson. All right, bye for now, and then I'll see you in the next podcast where we'll be doing some more transformations of log functions. All right, bye.